Hi everyone, welcome to the section on K-means clustering. So this is our first section on unsupervised machine learning. In this section, we will learn how to apply K-means clustering on the dataset. So K-means clustering is the most widely clustering technique used in unsupervised machine learning. So these are the topics which we are going to cover in this section. So we start with the definition of K-means clustering, and then we will discuss the intuition behind K-means clustering. Then we will understand K-means clustering step by step. That is, we will learn how to apply K-means clustering on a particular data step by step. Then we apply K-means clustering on a one-dimensional data. So you can see that we will start from the very basic, that is one-dimensional data. Then we move on to a 2D data. So after getting the understanding of K-means clustering on 1D data, then we will apply K-means clustering on 2D data. After that, we will also learn how to find the optimal number of clusters for K-mean. So there is a method known as elbow method. We will discuss this method in detail, and this method help us to find the optimal number of clusters. After performing the clustering, we will evaluate the performance of K-means clustering using a metric known as CH index. And finally, we have 3 projects of K-mean clustering where we apply K-mean clustering in Python, and we will learn how to implement K-mean clustering in Python. So I hope you will enjoy this section. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we are going to discuss the definition of K-mean clustering, the intuition behind K-mean clustering, and the steps involved in K-means algorithm. So let's start with the definition of K-means clustering. So K-means clustering is an unsupervised machine learning algorithm which partitions n observations of a data into K clusters in which each observation belongs to the cluster with the nearest mean. Now, there are 3 important terms in this definition which we need to understand. When we say observation, observation means number of samples in a dataset or number of data points in a dataset. K cluster, it means how many cluster we want in K-mean clustering, whether we need 2 cluster or 3 cluster. The nearest mean is the center point of a cluster. So the definition is in K-mean clustering, assign each observation the cluster with the nearest mean. It means K-mean clustering assign each data point to the cluster whose centroid is closest or near to that data sample. Let's understand this with this diagram. Now we have a figure. We can see that this is cluster 1, then we have cluster 2, and then we have cluster 3. So these are the data points, 3 data points which are grouped into 3 clusters. The centroid of each cluster is denoted with the yellow color. So centroid is considered as a center point of a cluster, and it is basically the mean of all the data points in a cluster. So this red point is assigned to this cluster because it is nearest to this centroid as compared to this centroid and this centroid. Similarly, if we see this green color data sample, this is assigned to this cluster because it is nearest to this centroid. So the centroid is called nearest mean. If I go back and I see the word nearest mean, it means that it is a centroid of a cluster. So if we have 200 sample and we want to partition them in 3 cluster, then n is 200. We can say that here n observation. So n will be 200, which is number of samples, and k is equals to 3, which is number of clusters in which we are going to partition our data sample. So this is an example of a K-mean clustering, and we understood the definition of K-mean clustering, that K-mean clustering assign each data point the nearest mean, that is the centroid which is nearest to that data point. So that centroid is nearest to all these red data points. That centroid is nearest to all these data points. That's why these data points are grouped together with this centroid, and that centroid is the mean of all these data points. So this is the intuition behind K-mean clustering. So what is happening? So this is the data set which is given to us to perform K-mean clustering. So this is the situation of K-mean clustering. What we want from K-mean clustering? So we want K-mean clustering to cluster this data set into group. So the important thing here is how K-mean clustering works. Now we can see that here K-mean clustering has grouped this data set into 3 different clusters. The other possibility would be that we might get 2 clusters from this data set. That is the cluster 1 here, and this is the cluster 2. But the thing is how we reach from this status to this status of clustering. Here, this is before clustering or before K-means, and here we are after K-means. So how we reach from this state of data set to this state? It means in order to reach from this state to this state, we have to apply K-means algorithm. So these are the steps of K-means algorithm. The first step is we have to select the value of K. We have to select the value of K, which is the number of cluster we want from dataset. Now, there are many methods of selecting K, which we will discuss. The first method is a manual method that we know in advance that we want to cluster our dataset into 2 clusters. We want to group our dataset into 2 clusters. In that case, we select the K manually. The other thing is there is an optimal method or there is a small algorithm to find the optimal value of K. So we will discuss that algorithm well in the coming slide. Now, if we have decided about the number of cluster, it means we have also decided about the number of centroid, because if there are 3 clusters, it means there will be 3 centroid. So the second step is that we create K centroids at random location inside the dataset. So we start with the random location and we see that as we move on with the K-means algorithm, these centroids will move inside the dataset to get the samples which are closely related to them. So basically we start with the K clusters, number of cluster, then we create K centroids at random location, and when we move on with the K-mean algorithm, these centroids will move to get the data samples or to group the data sample. We will see them in detail with the help of numerical example. Then we will compute distances of all data points to all centroids. So if we have 3 centroids and we have 200 data points, then we calculate the distance of all 200 data points to all 3 centroids. Then the step 4 is we assign each data point to its nearest centroid. Now suppose I have a data point whose distance from first centroid is 3, from second centroid is 4, and from third centroid is 5. So I will assign that data point to centroid 1, that is which is closest to that data point, which has the small distance to that data point. So in step 3, we compute the distances of all the data points to all the centroid, and then we will assign each data points to its nearest or closest centroid. Now, step 5 is important. Now we will move the centroid to new position, which is the average of all the data points. In point 4, the cluster or the centroid of all data points has been decided. Now we will take the average of data points in a cluster, and based on the average value, we will move the centroid to the new position. And then we will calculate the distance again. Then we will assign each data point again to the nearest centroid. That is, if you see in step 6, we will repeat from 3 to 5 until the algorithm is converged. When algorithm is converged, the algorithm will be converged when centroid will not move, and every time we will get the same points to the same cluster. So this is the method of applying K-means algorithm. These are the 7 steps of K-means algorithm. When algorithm is converged, your model is ready to work. So we apply this algorithm for K-mean clustering. In the next lecture, I will explain these 7 points with the help of a numerical example. So we will start understanding K-means clustering first with one-dimensional dataset and then with two-dimensional dataset. So I hope you understood the definition of K-mean clustering, the intuition of K-mean clustering, and the steps involved in K-means algorithm. When we apply these 7 steps on a numerical example, then you will get everything about the K-mean algorithm. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we are going to apply K-mean clustering on a 1D data, and we are going to solve a numerical example on it. If you remember in the previous lecture, we studied K-means algorithm. So these were the 7 steps or 7 points if we want to apply K-mean algorithm on any data set. So now in this particular lecture, we are going to apply the K-mean algorithm on a one-dimensional or 1D data. So this is my 1D data. I have selected a simple one-dimensional data having only 6 data samples. So since the data is 1D, I can simply plot this data on a number line. You can see this is the number line. So this is the position of 5 on the number line, 6, 9, 11, 18, and 22. So to start with, we are going to apply K-means algorithm on a one-dimensional data, and we have successfully plotted this data on a number line. Now we have to follow the step. So what are step 1 and step 2? Step 1, we have selected manually the number of clusters. So we have selected that we are going to start with 2 clusters. Later in this section, we will also study how to select the optimal number of clusters with some algorithm. But to start with, we are going to select manually the number of clusters. So here the clusters are 2. Since clusters are 2, therefore we have to select 2 centroids randomly as well. So the position of the 2 centroids which we have selected is 7 and 12. So now we can see the complete diagram. We have a number line, we have plotted the data samples, and we have also placed 2 centroid on this number line, the centroid 1 at 7 and centroid 2 as 12. They are shown with these red square and blue square respectively. So these were step 1 and step 2. So what is step 3? So if you remember, in step 3, what we do is we compute distances from all data points to all centroid, and then we assign each data point to its nearest centroid. So basically, first we have to calculate the distances, and based on that distances, we assign each data point the nearest centroid. So if I start calculating the distance here, if I start calculating step 3 from here, so distance of 5 with 7 is less as compared to distance of 5 with 12. So basically, I have to calculate the distance of every data point with every centroid. So I have 2 centroid. So start with 5. 5 is nearest to 7. This is very intuitive, and you can do it directly without any calculator. 7 minus 5 is 2, whereas 12 minus 5 is 7. So 5 is close to this 7. Similarly, 6 is close to this centroid in terms of distance as compared to this. Similarly, 9 is also close to this centroid. 11 is close to this centroid. 18 is also close to this centroid because 18 minus 12 is 6 and 18 minus 7 is 11. So 6 is smaller than 11. Therefore, this 18 is close to this. Similarly, 22 minus 12 is 10 and 22 minus 7 is 15. So what we have decided according to the distance that these 3 data points are close to this cluster and these 3 data points are close to this cluster. So based on this, we have done step 3 and 4. We have calculated the distance and we have assigned each data point a cluster. So these are my step 3 and 4, which I have already done. I have computed the distance and I have assigned each data point a cluster or a centroid. So based on step 3 and 4, this is our clustering. We have started K-mean clustering. Now step 5 is very important. If we see the step 5 of K-means algorithm, move the centroid to new position. Now we have to move the centroid. We have assigned each centroid since we have selected the centroid randomly. So here the algorithm is not converged. Now we have to move the centroid so that every data point should assign a correct cluster. So how to move? Move the centroid to new position, which is the average of all the data point in a cluster. We have 2 clusters now. Calculate the average of all the data point in a cluster. So what is the average of these 3 points? 5 plus 6 plus 9 divided by 3. And the average of this 3 point will be 11 plus 18 plus 22 divided by 3. So here are the averages. Now the new position of centroid 1 is 6.7. Previously it was at position 7. The new position of centroid 2 is 17. Previously it was at 12. So now we have moved the centroid. Now, after moving the centroid, which was step 5 of the algorithm, the step 6 is to repeat from 3 to 5. Now, I have to calculate the distance of all the points again with all the centroid. Now, the distance of 5 with 6.67, this is less as compared to 17. So 5 is assigned with this centroid. Similarly, 6 and 9. Now, what about 11 now? Now, 11 is far away from this as compared to this. If I calculate the distance, 17 minus 11 is 6. But 11 minus 6.67 is 4.33. Since 4.33 is less than 6, it means now 11 will move to this cluster. Previously, 11 was in cluster 2 or in blue cluster or with the second centroid. Now the centroids of the cluster have moved according to the mean of the data point. Now with this new shift of the centroid, now this 11 will move to cluster 1 because the distance of this 11 is now less with cluster 1 centroid as compared to the centroid of a cluster 2. Here is the new grouping or new clustering. Now the 4 data points are in cluster 1 and 2 data points 18 and 22 are in cluster 2. Now we have to move the centroid again and we can see that we will get the new position according to the average. So what is the average of these 4 points now? The average of these 4 points is 7.75 and the average of these 2 points is 20. Now it was 6.67 previously and 17. The new positions are 7.75 and 20. So the next step is to calculate the distance of each point with the new positions of the centroid and form the clustering again. We will repeat until centroid will stop or they will not move. So still they are moving. At the start, they were at 7 and 12. Then they moved to 6.67 and 17 respectively. And now they have shifted to 7.75 and 20. So they are still moving. They are still trying to assign each data point a correct centroid. Now, what is the new grouping or new clustering now? This 5 is close to this, 6 is close to this as compared to this. So we can see that very easily. Now we will again get the same grouping, that is these 4 points will be in cluster 1 and these 2 points will be in cluster 2. So we are still getting the same grouping. Centroids have moved. We can see that previously it was at 6.67. Now it is at 7.75. Previously this was at 17 and now it is at 20. The centroids have moved, but now the clustering is same. So this is our new clustering. Now we can see that again these 4 points are in cluster 1 and these 2 are in cluster 2. Now again calculate the mean. So we can see that now the centroids are not moving and we are again getting 7.75. This was 7.75 and 20 and now we are again getting these 2 points. Now we can see that the centroid is stopped moving because the algorithm has converged and this is our final solution. So we can see that these 4 points out of these 6 points belongs to cluster 1 and these 2 points belongs to cluster 2. So in this way, the algorithm has converged and our model is ready to use. So in this lecture, you learn how to apply K-mean clustering on 1D data. You apply all the 7 points and you see that every time when you calculate the average of data point in a cluster, we get the new value, that is the new position of the centroid. When you do not get the new position of the centroid, it means your algorithm is converged and now your clustering has been done. I hope you understood this lecture. Thanks for listening and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we are going to learn how K-mean algorithm is applied to a 2D data. And we will learn this with the help of a numerical example. So this is the intuition that how 2D data looks like. We can see that this is the scatter plot of a 2D data. Every data point in this data set has 2 dimension or 2 features, that is one along x1 and another along x2. So this is the application of K-means algorithm on a 2D data. So that is our starting point. We can see that we have a 2D data. So we have selected 2 clusters. It means we have 2 centroids. So the next step is that we have to put these 2 centroids randomly in a data set. And when the algorithm will converge, we will be here. So this is the converging point. that this data will be divided into two groups or two clusters. Now, in this data set, there are so many points. So we are not going to use this data set in our numerical example. This figure just show you the concept that if you have a 2D data set and you are starting with two cluster, then your end will be look like this. This will be your converging point, and you can see that your centroids have moved and they have formed the cluster and they have selected the points according to the nearest distance. So this figure shows the intuition about the convergence of K-mean algorithm on a 2D data. Let's take an example with less number of data points. So this is a numerical example. Here we have 6 data points from x1 to x6, and every data point has two features or two dimensions, that is small x1 and x2. Since our data points have two dimensions, therefore the centroid will also have two dimensions. So this is our data set. So we will start with k is equals to 2. So we have assumed that there are two clusters and therefore we have two centroids. So these are the random locations of the centroid and these are our 2D data points. This is the scatter plot of data, 2D data along with the centroids. So we can see that here is our x1 according to its magnitude and according to its dimension. So x1 dimension or its coordinates are -2 and 3. So we can see that x1 is at the intersection of -2 and 3. Similarly, every point is plotted according to its 2D coordinate. And similarly, these two centroids are also plotted. If we see that the first centroid coordinates are 1 and 3, so this is our first centroid. So it is at the intersection of coordinate 1 and coordinate 3. So this is the scatter plot of data sample as well as centroid. So this is the starting point. So the next step is to calculate the distance of every point with every centroid. So we will start with x1. So the step should be the distance of x1 with centroid 1 and the distance of x1 with centroid 2. So how to calculate this distance? Now be careful, this time a distance will not be as easy as it was in 1D because we have a 2D data. So to calculate the distance in 2D, we have to use Euclidean distance equation. So we are going to calculate the distance of point or data sample x1 from both centroid. We will use x2 minus x1 square and y2 minus y1 square, this Euclidean distance. So there is a square on each term, so that distance should be positive. So how to calculate x2 minus x1? Where is x2, where is x1, and where is y2 and y1? So the first step is, since we are going to calculate the distance of x1 with first centroid, which is mu1, so the coordinates of x1 are x1, y1, and the coordinate of this centroid are x2 and y2. So x2 minus x1 will be 1 minus -2, and y2 minus y1 will be 3 minus 3. So here x2 minus x1 is 1 minus -2, this will be 3, and 3 minus 3 is 0. So you will end up with root 3. So you will end up with 3. So where d11, this d11 is the distance of x1 from mu1. So the distance of x1 from the first centroid is calculated and it is equals to 3. Let's calculate the distance of this same point but with centroid 2. So this is centroid 2 mu2. Here this will be x1, y1, and now these points will be x2, y2. So the distance will be x2 minus x1, y2 minus x1. So this will be 2 square plus 4 square, and we will end up with root 20, which is 4.47. So the distance of point 1 or the data point 1 with second centroid is 4.47, which is greater than 3. It means x1 is close to first centroid as compared to second centroid. Since x1 is close to first centroid, therefore x1 belongs to centroid 1, or x1 belongs to the cluster whose centroid is mu1. If I go back, we can also confirm from the scatter plot that x1 is close to mu1 as compared to mu2, and it is verified after the calculation also. So the decision about x1 has been made that x1 belongs to mu1. Let's do it for x2. So the distance of x2 from both centroid is 3.6 and 1.4. This is the distance of sample point 2 with first centroid and sample point 2 or data sample 2 with second centroid. Here I am showing you the distances directly. I am not showing you the calculation. Now you know the Euclidean distance. You know how to select x1, y1 and x2, y2. So you can easily find these distances now. So the decision is that 1.4 is less than 3.6. It means the distance of second point is close with mu2 as compared to mu1. Therefore, x2 belongs to mu2, which is the centroid of the second cluster. Now we repeat these calculations for all the 6 points. For x3, D31, the distance of sample 3 or data sample 3 with first centroid is root 5 and with second centroid is root 10. Since root 5 is less than root 10, therefore x3 belongs to mu1. Similarly, x4 also belongs to mu1 because its distance with mu1 is less than with mu2 or with the second centroid. Here about x5 and x6. So x5 belongs to mu1 and x6 belongs to mu2 because the distance of x6 with second centroid is less as compared to the first centroid. Now all the distances has been calculated and centroids has been assigned to the data sample. Now it's time to go to the scatter plot and plot the clusters. So this is after the first iteration, and we can see that x1, x3, x4, x5, these 4 points belongs to cluster 1, and x2 and x6, these 2 points belongs to cluster 2. Now, since we have selected the locations of these centroid randomly, now it's time to move the centroid by calculating the average of data points inside the cluster. Now, how to calculate the average of these 4 points so that we can move first centroid, and how to find the average of x2 and x6 so that we can move the second centroid as well. Now, how to calculate the average in 2D? So this is our point. These are our 4 points in mu1. This is point x1, x3, x3, x4, and x5. And how to find the average? So on average, you have to add the coordinate which are at the same position. Like you have to add -2, -1, +2, and +4. And since they are 4 points, then you have to divide it by 4. Then you have to separate it, this coordinate with comma. Then you have to add 3 + 2 + 2 + 1, and then you have to divide it by 4 again. So in this way, you will be able to calculate the average position of a first centroid, which is 0.75 to 2. Now the average of these 2 points, which is x2 and x6, is 1 and -0.5. So in this way, we have find the new positions for mu1 and mu2. So this is the second iteration, and we can see that now the centroids have moved. The points do not move. So keep in mind, which I already told you during the previous lectures, that in K-means, the centroid moves according to the average value of data points in a cluster. Now the next step is again calculate the distance of x1 with these 2 centroids, then x2, that is the distance of all points with all centroids, and then again you have to assign each data point a new centroid according to the nearest distance. So I am not going to show you. I leave it to you. This will be a very good practice for you. So I request you to take a paper and a pen and start calculating the distance of every data point with every centroid. When you are done, you will reach up to this point. So this will happen now. Now you can see that there are only 3 points in each cluster. Previously in cluster 1 or in red cluster, there were 4 points. Now there are 3 points according to the new calculation. So this is after the end of second iteration. Now the next step is again to calculate the average of these data points inside the cluster, and then move the centroid according to the new position. So you learned in the previous lecture, which was the implementation of K-mean algorithm on 1D data, that you have to keep calculating the averages of the centroid until the algorithm is converged. The point of convergence is achieved when centroid will not move further. So after this, you will have to calculate the position of the centroids again by calculating the average of each data point. So this is our third iteration. So I am not going further. This is the new position of mu1 and this is the new position of mu2 by taking the average of the data point present in the cluster. So I hope you understood this lecture. I request you to complete these calculation. Maybe you need 4 iteration, maybe you need 8 iteration, but it will give you an insight of K-means algorithm, that how K-means algorithm works. Previously, you learn how K-means algorithm works and converge on 1D data. Here you are learning how 2D data works or how K-means algorithm apply on a 2D data. So please take a paper and pen and start calculation until to reach the convergence. I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we will discuss the objective function of a K-mean algorithm. So this is the objective function, which is also known as the loss function or the cost function. So we have learned so many times about the objective function of different algorithms in this course in the previous sections. So basically, the definition or the concept of objective function is that what algorithm is doing or what we are trying to achieve with the help of the algorithm. So this is the loss function or the objective function of K-means algorithm, where M is the total number of data points in a data sample. So basically, the concept of algorithm is that for every data point, we calculate the distance between the data point and all the centroid. So xi is the I sample of the data sample here, and uk is the centroid of the kth cluster. So if we have k cluster, it means we have to calculate the distance of every point with all the k centroid, and then based on the nearest distance or the smallest distance, we decide the cluster of the data point. So this is the simple objective function where we are calculating the distance between the points and then we are squaring the distance so that we can get the positive value. So this is the objective function, and then we will repeat this for every data point. The nearest the distance of a data point is with the centroid, so that centroid will be assigned to that data point. So I hope you understood this short lecture. It was all about the explanation of the objective function, which is like the calculation of a distance between the data point and the centroid, which you have seen in the previous lectures where we calculate the distances for a 1D data and a 2D data. So I hope you understood this objective function. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we will learn how to choose right number of cluster using elbow method. Previously, we select number of clusters manually. We saw that in 1D and in 2D examples where we implement K-means algorithm, we selected the number of clusters manually. Here we are going to learn an elbow method to select the optimal or right number of cluster. So the first thing is we need to learn what is WCSS, which is within cluster sum of square. So let's learn the definition first. WCSS means calculate the distance of every point in the cluster with its own centroid, then square it, then add it to another distance. Same is repeated for every cluster, and then add all the distances to find WCSS. So this is a big definition. There are a lot of things which we need to understand. So this is the equation of WCSS, which is within cluster sum of square. So if you see, this equation is written only for 3 clusters. However, it can be extended to any number of clusters. So how to calculate each term in this WCSS equation? First of all, look at the term number 1. This is about the cluster 1. So mu1 is the centroid of the cluster 1, and here xi are the number of data points only in cluster 1. So the first term is only related to cluster 1, then the second term is only related to cluster 2, and the third term is only related to cluster 3. So xi here is not all the data samples of a data set. Xi are those data samples which are in cluster 1. Similarly, here xi means those data samples which are in cluster 2, and here which are in cluster 3. Mu1, mu2, and mu3 are the centroid of these 3 clusters. So here is the description that WCSS is some square distance within the cluster. And xi is every point in the cluster, and mu1 is centroid of cluster 1. Now, how to understand this? Look at this figure. So this is our cluster 1. First, we will calculate the distance of this red point with its centroid. Then we square that distance. Then we calculate the distance of second red point with this centroid. We square the distance and then we add it to the first distance. We repeat these steps for every data points in cluster 1, and in this way we calculate this quantity. You see, this is the distance. We square the distance, then we calculate the distance of second data point in the cluster with the centroid. We square the distance, we add it to the previous distance. In the similar way, we calculate the distance of all the data points with its centroid. We square them and we add them. So in this way, we calculate the first term. Same is for cluster 2 and cluster 3. And finally, when we add all these terms, we will get WCSS. So what is the advantage of WCSS, or what are the important points related to WCSS? So these are the important points. The most important point is highlighted here. WCSS decreases with the increase of cluster. It means if we increase the number of clusters, the value of WCSS will be decreased. So let's start point by point. If there is only one cluster, then there is only one centroid. Hence, the distance between data point and cluster is large. So look at this figure. Suppose we have only one centroid and it is at this location where my cursor is moving. So if the centroid is only one and it is at the middle, then the distance of this red point from this centroid is very large. Similarly, the distance of these green point from this centroid is very large. In general, the distance of every point to the centroid is very large. So the distance will be large, and so is WCSS. So if we have only one cluster, the value of WCSS is very high. If we increase the number of clusters from 1 to 2, then data points will have two centroid. In that case, if we have two centroid, it means we have two group of data. And now we do not need to calculate the distance of every point with every centroid, because we know in WCSS, we have a centroid and we only calculate the distance of sample points with their respective centroid. In that case, the distance will decrease. So if I go back and suppose we have these two clusters only, in that case, the distance associated with this red and this yellow centroid is less as compared to the previous situation where there was a single centroid and it was located somewhere here. So if we have two clusters, then every data sample, the distance of every data sample is measured with its respective centroid. So the distance will be decreased as compared to one cluster situation, and so is WCSS. So when we increase the number of cluster from 1 to 2, the WCSS decreases with the increase of cluster. So let's keep on increasing the number of cluster and reach to the point or stage where the number of cluster is equal to the number of data point. So what happens if we have 10 data points and we have 10 cluster? It means every data point has its own cluster and every data point is also the centroid of that cluster. So if you calculate the distance between data point and centroid, it means you are calculating the distance of a point with itself, which will be a 0. So WCSS will also be a 0. So if you keep on increasing and reaching to the stage where every data point has its own cluster, your WCSS is 0. So the takeaway point is that if we increase the number of cluster, WCSS decreases. So this is the elbow plot. You can see that this is a plot between WCSS and cluster. So this plot is only for 5 cluster. Now, when we are at cluster 1, we can see that the value of WCSS is very high, which we have just learned. Now, when we increase the clusters from 1 to 2, we can see that this value decreases significantly. Now, when we increase from 2 to 3, value also decreases significantly, but this decrease or this slope is less steep as compared to the previous one. Then we move from 3 to 4 cluster, the value is still decreasing, but now it is starting to become a flat curve. And we can see that as we increase the number of cluster, WCSS decreases, but the percentage or amount or the ratio of decrease is very low and very less significant. So what are the optimal number of cluster for this elbow curve? So we have selected that 3 is the optimal cluster. Why? Because before 3, the change in or decrease in WCSS is very significant, and after 3, it is very less. You can also take a 4 number of cluster and 3, but here a 3 is more optimal cluster. We see in the next lecture that if we wrongly select the optimal cluster, we also have a check to correct the number of cluster. So here there might be a confusion between 3 and 4 cluster, but we are clear the clusters are either 3 or 4, and most probably it is 3, because after 3 the decrease in WCSS is very less, and this decrease become flat as we go further in the cluster direction, or as we increase the number of cluster. So in this lecture, we learn the elbow method. We see the elbow method or elbow curve is a curve between WCSS and the number of cluster. This WCSS decreases as the number of cluster increases. So we select that point after which the WCSS does not decrease much or starting to become a flat. So that number of cluster will be the optimal cluster. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we will see how we can evaluate K-means performance. We have already learned how to select the optimal number of cluster. Now, after selecting the optimal number of cluster, we have implemented the K-means algorithm. So this evaluation will be started when your algorithm is converged or you have done with K-means clustering. So when you have done with K-means clustering, you need to calculate the index known as CH index. So it is known as Kalinski-Harabas index, and in short, you can remember it as CH index. This is also known as variance ratio criteria. It is the ratio of two matrices. It is the ratio of scatter matrices between the cluster and scatter matrix within the cluster. So we have to calculate these two matrices in order to find the CH index. The higher the CH index, the better is the performance. It means the value of SB or the value of scatter matrix between the cluster should be higher than the value of scatter matrix within the cluster. So that will be our ideal situation. Now look at these two convergence points. Here the algorithm is converged and we have two separate clusters. Here the algorithm has also converged. This is our another example, and we also have two clusters. Now we can see that this clustering is better as compared to this clustering. Why? Because the separation of the cluster is very large, very clear, and very obvious. Here it seems that the clusters are trying to overlap on each other. So what will happen? What is SB and SW for this matrix? So basically, SB is between cluster scattering or between cluster dispersion. So we clearly see that here, this matrix will be high as compared to within cluster. So basically the demand of CH index is the value of SB should be high than the value of SW. Here we can see that the distance between this point in red cluster and this point in blue cluster is very large. So the distance of this point with this point is very large as compared to the distance of this point with the other point within cluster. So the requirement of CH index is that the distance between the points within the cluster should be very less as compared to the distance between the points between two clusters. Now here there is a problem. Here if we consider this point, this data sample, its distance is almost same with the other point in its own cluster and with the point in the second cluster. So this is not an ideal situation. The ideal situation is the distance within the cluster should be less and distance between the cluster should be high. Here the distance of the data points between two clusters is very high. They are very well separated, and distance within the cluster is very less as compared to the distance between the cluster. So this cannot be obvious very much in this form of example. Here the distance between the 2 points between two cluster is almost same as that of within the cluster. So here the CH index might be less than 1, and here it must be greater than 1. So this is the requirement of CH index. Let's solve a small example and find the value of CH index or find the value of SB and SW, which are scatter matrix between the cluster and scatter matrix within the cluster. So here I am taking 4 data samples only. So this is another way of representing a 2D data points in terms of feature vector. So X1 is 2D, X2 is also 2D, so X3 and X4 are, and this is the way of representing a 2D sample points in terms of their 2 features. Now, the clustering has already been done, and X1 and X4, these 2 data points belongs to cluster 1, and X2 and X3 belongs to cluster 2. Now we can evaluate the performance of clustering. The first step is to calculate the means of the cluster. This is our first cluster, and here we are denoting the mean by M1. So the equation is very simple. Like whenever we calculate the mean of 2 points, we have to add them and divide by 2. So X1 plus X2 divided by 2. So here the second point is X4. So this is the value of X1. This is the value of X4. We can add them and then divide by 2. 4 plus 5 is 9 divided by 2. 5 plus 0 is 5 divided by 2. This is the mean of the first cluster, and this is the mean of the second cluster. So they are denoted by M1 and M2. So you have to remember that M1 and M2 are the mean of cluster 1 and cluster 2 respectively in our numerical example. Now, first of all, we are going to calculate within cluster 1. Within cluster 1 scatter matrix. So the equation is X1 minus M1. So X1 is first data point and M1 is the mean of first cluster. Here we are taking the transpose of this term. Then the second point in cluster 1 is X4. So we are again subtracting the mean of cluster 1 from X4, and here we are taking the transpose. Now the important thing is how to calculate the term X1 minus M1. So the calculation is very simple. This is X1, subtract the mean of the first cluster. So if you subtract 9 by 2 from the 4, 4 minus 9 by 2, it will be minus half. Similarly, if you subtract 5 by 2 from the 5, you will get 5 by 2. So here you calculate X1 minus M1, which is minus half and 5 by 2. So you put this value here, that is minus half and 5 by 2. Then you take the transpose of this value. This is the transpose. Similarly, you can calculate X4 minus M1 and X4 minus M1 transpose. So multiply these two matrices and these two matrices and then add, you will get S1. So this is S1. Here we use the points inside the cluster 1 and mean of cluster 1. Similarly, we can find scatter in cluster 2 by the points inside the cluster 2 and mean M2 of a cluster 2. So by doing all the steps which we did previously, we get up to this matrix. Now the final within cluster matrix SW will be the sum of these two matrices. Add half, with half you will get 1. So this is the sum of within cluster, that is, this is SW matrix. This is the scatter matrix within the cluster. Now it's time to calculate the between cluster scatter matrix. Now for between cluster, you have to calculate the mean of all the 4 points. So these are our 4 points in the data set. We add them, divide by 4. So this is the mean of all the data points or all the data set. Now between cluster equation is N1 multiply M1 minus M, M1 minus M transpose, N2 multiply M2 minus M, M2 minus M transpose. Now M1 is the mean of cluster 1 and M is the total mean. Here is the total mean. Now you have to subtract these two mean. This is the value when you do a subtraction. This is the transpose of this term according to this. N1 is the number of data points with cluster 1. So we have 2 data points in cluster 1, therefore N1 is 2, and 2 data points in cluster 2, therefore N2 is also 2 for this particular example. Similarly, you have already calculated M2, which was the mean of the cluster 2. Now subtract the mean of the total data points from M2, and here is the transpose. So just follow this equation step by step. You know how to calculate, how to subtract 2 by 2 matrix or a matrix having 2 dimensions. This is very easy to do. Now solve this term and add them. You will get between cluster matrix. Now this is between cluster matrix. and this is within cluster matrix. Now, how to solve that? If I go back and see the equation, we have to divide it. Now, how to divide the matrix? So we will not divide the matrix directly, but we will find the trace of the matrix. So what we will do, we will add the diagonal values. The trace is the diagonal value. So I will add 17 plus 1 to get the trace of SW, and then I will add 16 plus 0 to get the trace of SB. So here is the equation of a trace. So the definition of trace is sum of diagonal element of any matrix S. So if you want to find the trace of SW, it will be the sum of all the elements present at the diagonal of SW matrix. So what will happen? The trace of this matrix is 16, SB, and the trace of SW is 18. So when we put this value in this equation, what we will get? So this is 16 and this is 18. So here our CH index is less than 1, which is not an ideal case, because the higher the CH index, the better is the performance. So in this lecture, you learn how to evaluate K-means clustering. When you have done with K-means clustering and when your algorithm is converged, it's time to calculate the CH index, which is the metric used to evaluate the performance. This matrix requirement is that SB should be higher than SW. That is, between the cluster, the separation should be large as compared to within the cluster. We see with a numerical example how to calculate these two matrices. And after calculating these two matrices, we have to find the trace of the matrix in order to calculate these value. So I hope you understood this lecture. When we apply K-mean algorithm, or when we implement K-mean algorithm in Python, you don't need to worry about these sort of calculation. There is just a one line of code available to calculate the CH index. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we are going to implement K-mean algorithm in Python. So here I am in my Google Drive, and this is my course folder. Let's click on this. So inside this course folder, I have three major sections of the course. So here I am at unsupervised machine learning. And inside unsupervised machine learning, we have K-means clustering. Let's click on this. And here is my project one. So basically in this lecture, I am going to solve a project one, which is on K-means clustering. That is, I am going to implement K-means clustering in Python. Let's click on this. And we are going to open this file in our Google Colab environment. So we can see that the file is opened in our Google Colab environment. So the first step is to import all the necessary Python libraries. These libraries are NumPy, Matplotlib. From Matplotlib, we can import style. So all this is very standard stuff you have seen many times in this course before. So let's run this cell to import these important libraries. So the next step is that we are going to generate our own dataset. We are not going to import any dataset from any folder. So here we are using sklearn to generate a data. In our many previous sections, we know that with the help of sklearn.dataset, we can generate data. There are a lot of functions inside sklearn.dataset that help us to generate data. So here we are importing make blob. So how make blobs work? This function consists of random generation, and this function will generate random data for us. Here there are three inputs which we are going to give to this function. The first is number of samples. Now, how many samples we need, how many features we need. Here we are putting 200 samples and 2 features, and this is a random state. So you know from the previous lectures that random state needs to be set if we want to generate data, if we want to generate same data every time. So what happened is that make blob is a function that generates random data. If we do not set this seed or this random state, every time we run this cell, we get a different samples of data. So if you want same samples of data every time you run this cell, you need to put the random state equals to any value. You can put it 0, 1, 2, 3. So this 42 is not a special number. You can put it any value here. So if you want to see in detail what make blob is doing, so you can call help function on it. If I run this cell, if I uncomment this first and run this cell, I can see the document. No, so first I have to import this. then I can see the document. So here we can see that if you go here, the make block function needs few inputs, that is number of samples, centers, number of features, and random state. You can also put centers equals to none. So you can give these 4 inputs to a make block function. In this way, you can generate a random data. But if you put random state equals to 0 or to any other value, you will be able to generate the same samples of a data. So this was a doc string of a function make blob, which you can see by calling a help function on make blobs. So I can commit it, put in the comments, and now move further. So here I am going to generate a data. My samples are 200. Number of features are 2 and random state is 42. So in order to understand this more clearly, let's reduce the data size first. So the number of samples are 5. So what happens if I run this cell and see the data? So these are my 5 samples. So if you can see these samples will remain the same whenever the random state is 42. So if I run this and I run this again, you can see that every time I run this, I get the same samples. But if I remove the random state completely from the function, every time I run this cell, I will get different samples of a data. So you can see that every time I run this cell and see the data, it is different from the previous data. So if you want to generate same samples of data every time, then in that case, you have to put a random state equals to some number so that you can generate same samples of data every time you run this cell. So now if you run this cell, you can see this data. Now make blob has generated a data for us. Look at the type of the data. Now it is saying this type is a tuple. Now what is tuple? We have learned about the tuple in our section of Python crash course. So if you don't know anything about the tuple, it is highly recommended to go back to that section and study the lecture on tuple. So we can see that this tuple, if we check the length of the tuple, it is 2. So how it is 2? So basically this data is a first part or first element of a tuple, and these labels, these integers, these labels are the second element of the tuple. That's why when we check the length of the data or a length of a tuple, it is 2. So it is very important to understand the data. Whenever you read a data and whenever you generate the data, the first step should be to check the type of the data, the length of the data, the shape of the data, and other characteristics of the data. So here we learn that when we generate a data using a function make blobs, the type of a data is a tuple and its length is 2. The first element is the features, are the number of features. You can see that the number of features are 2. So this first column is a first feature and this is a second feature. Number of samples are 5, and we can see that there are 5 rows or 5 samples in a data. These are the labels of a data. So in this case, we see that make blobs generate a data in the form of tuple. Now, since I am going to plot or I am going to cluster the data, for clustering, I don't need labels. Since I do not need labels, therefore I only need features. So in order to extract feature, I will put an index 0 to the data and I will get the value of x. So if I run this cell and if I want to see x now, we can see that this x is the feature matrix. And the most important thing is now it is in the form of numpy array. Let's run this cell to check the type of the data. So in this way, we generated the data with the help of make blobs function, which is present inside the library sklearn.datasets. We see that this function generates data randomly. And if we want to generate same samples every time, we have to set the seed and we have to put random state equals to some value. The data generated is in the form of tuple whose length is 2. The first element is the feature and the second element are the labels. Since we do not need labels in clustering, we only need features. Therefore, here we have extracted the features. The extracted features are in the form of numpy array. So this is the important observations about the data. Now put the number of samples equals to 200 because 5 samples are very less if we want to see the clusters. So let's run this cell again for 500. And now again, the type is tuple, the length is 2, and we want to extract the features. And now we will have 200 samples. Now we can see that here we have lot of features. We have 200 samples. Now the type is again NumPy array. So we have generated the data. We have gone through the data. We have do some data analysis, and we reach to the point where the samples and features are now in the form of NumPy array. Now we have to go through the elbow method. In a theory lectures, we have learned that elbow method is very important if we want to find the optimum number of clusters for K-mean. But another important thing is in elbow method, we use WCSS, which is within cluster sum of square. So first we calculate within cluster sum of square, then we plot within cluster sum of square against the number of cluster and see the elbow. And from the elbow curve, we will be able to find the optimal number of cluster. So the first step is that we have to suppose an empty list of WCSS, because we are going to run a for loop 10 times. If you see the range of the loop, it will run 10 times and it will calculate 10 value for WCSS. Therefore, we start with the empty list. When this for loop will calculate the 10 values of WCSS, they will be stored inside this empty list. So this line of code will run the for loop for 10 times. Here I am instantiating the K-mean function or the K-mean object. So its input is number of cluster. So number of cluster is the value of I. So this loop will run for 10 times. So it means we will calculate WCSS for 10 cluster. Init, this is the method. Init is K-means plus plus. So the algorithm we are going to use is K-means plus plus. And init is auto. Now what this function is doing basically, or what this input is doing, basically it is creating the initial location for the centroid. We know from our theory of K-means that after selecting the clusters, we need to set the random location of the centroid. So this function or this input will set the random location of the centroid automatically. And this is our random state. So after this, I will get the K-mean function and I will fit this K-means to my feature X. When it will be fit on feature X, I will be able to find out a quantity known as K-means.inertia. This K-means.inertia will give us WCC, that is within cluster sum of the square. So this is the line of code which is going to generate WCSS for 10 different clusters. Here you can put 20, you can put 50, as much as you can, but I am going to check WCSS for 10 clusters only. Here I am input the function K-means, and these are the 3 input parameters. Then I'm going to fit, you know about the fit function, that it is going for training. And then I will get WCSS from here, that I will append with WCSS so that it will store in the empty list. So the append function, you have already learned about the append function in the previous sections, and also in the section of Python crash course, we study the lecture on the lists. So if I run this cell and then I run this cell, I can see the 10 different values. So these are the 10 different value of WCSS, that is for cluster 1, for cluster 2, for cluster 3. If we see these value, we can see that for cluster 1, WCSS is high. And for the last or the 10th cluster, it is very low. If we recall the lecture on WCSS, we know that it is inversely proportional to the number of cluster. As we increase the number of cluster, the value of WCSS decreases, and we can confirm from this value inside the list of WCSS. Now it's time to plot WCSS against the cluster. So here we are going to plot, this is the figure size. We are going to plot WCSS against the number of cluster. This is the range. This is the number of cluster from 1 to 10. This is the title of the plot. The X label is number of cluster. The Y label is WCSS. Let's run this cell. So if we run this cell, we get an elbow method. We get a very clear elbow curve. From this, we can easily find the optimal number of cluster. If we see to this point, we can see that this is equals to 3. So this is the optimal value of WCSS, or the number of cluster. Before this 3, we can see that there is significant drop in the value of WCSS. And after number of cluster is equals to 3, this drop becomes flat, or the drop is very rare or very less. It means this is the point which is the turning point for WCSS, because before this point it drops significantly, and after this point it becomes flat. So the number of cluster will be 3 for this project. So in this lecture, we are learning how to generate the data using a function makeBlob. We generated our own data set. We did not import any other data. So we have 200 samples and 200 features, and here we have converted this data into the form of NumPy array. We know that initially it was in the form of tuple, and now it is in the form of NumPy array. Then we apply elbow method. We plot the elbow curve, and from elbow curve, we see that the number of cluster for this K-mean implementation should be 3. So I stop this lecture here. I will continue in the next lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In the previous lecture, we have found that we need 3 clusters to implement K-mean algorithm, and we found the number of clusters using elbow method. Now it's time to apply K-means algorithm for 3 clusters. So here we are going to applying K-means clustering. So the first step is to import K-means from sklearn.cluster. Now we are going to instantiate this object K-means. So the input parameters are number of cluster, which are 3, then the algorithm, which is K-means plus plus, then init is equals to auto. So this input parameter will select the random location of a centroid. We learn in our theory part of K-means clustering that the number of centroids are equal to the number of cluster, and we have to randomly select the initial position of the centroid. So this input parameter will do this for us. This is the random state. Let's run this cell to instantiate K-mean. Now it's time to fit this K-mean object to our data and get the predictions from our data. So X is our data, and K-means.fit.predict will give us the predictions. Now, what predictions are doing here, and what is the importance of prediction here? Let's run this cell to see the predictions. If we see the predictions, there are 3 values, 0, 1, and 2. 0 represent the cluster 1, 1 represent the cluster 2, and 2 represent the cluster 3. So basically, ypred are the cluster values. Ypred is telling us that our first data sample belongs to cluster 3, our second data sample belongs to cluster 1, and our third data sample belongs to cluster 2. So these are the cluster values with respect to the data samples. So since we have 200 data samples, these are 200 values. If I run this cell to check the shape, we can see that the shape of ypred is 200 because the number of samples in our data is 200. Now, out of these 200, how many samples belongs to first cluster? So in order to check this, we have to put ypred is equals to 0. 0 here represent the first cluster, because we know in Python the index starts from 0. And if we sum all the values of ypred, which is equals to 0, we get 67. It means out of 200 sample, 67 sample belongs to cluster 1. And how many samples belongs to cluster 2? Then we have to replace this 0 by 1. If I run this cell again, I will get 66. It means the number of samples belongs to cluster 2 are 66. What about cluster 3? Now replace this 1 by 2 and run this cell again. Now we can see that 67 samples belongs to cluster 3. So if we add 67, 67, and 66, we get 200. So in this way, these 200 samples will be divided or will be grouped into 3 clusters. And we see that how many samples belongs to cluster 1, how many samples belongs to cluster 2, and how many samples belongs to cluster 3. Now, If I replace it back to 0, so there are 67 samples of data belongs to cluster 1. Now, something is very important to remember here before plotting. So basically, if we want to see the samples which belongs to cluster 1, then we have to index this ypred is equals to 0 through our sample. So this term will give us the data samples of X that is belongs to cluster 1. So we have 67 sample of X which belongs to cluster 1. If I run this cell, so these are the 67 samples out of 200 that belongs to cluster 1. This is the first feature or first dimension of the data, and this is the second feature, because we know from the previous lecture that there are two features in our data. If I want to check the shape, so I can see that the shape is 67 by 2. The reason is that there are 67 samples that belongs to cluster 1, and we can confirm with the help of shape. Now there is another quantity. So these are the 67 samples which belongs to cluster 1. Now there is another quantity, ypred equals to 0, 0. So what I will get if I run this cell? Now this is very important. If I run this cell, I will get the 67 values of the first feature. There are two features here. You can see that there are two features. This is a feature 1. If I want to extract only feature 1, then I have to put one more 0 here, because that 0 will indicate the first feature. So if I write ypred equals to 0, this first 0, this is very important to remember. The first 0 represents the cluster number, and the second 0 represents the feature number or a column number. So this second 0 represents the first column, because the index in Python starts from 0. So if we want to represent the first column or first feature, we have to use 0. So if you can see that the first two values are minus 5.12 and minus 2.7. So you can confirm this, that these values are minus 5.12 and minus 2.7. If we want to see these feature in the shape of column, we can convert it into column by using a reshape function, minus 1, comma 1. If I run this cell now, you can see that this is the first feature of the data. So very important thing you need to remember is about these two zeros. The first 0 indicates the cluster number, and the second 0 indicates the feature number. Now, if I replace this second by 1, then what will happen? If I replace it by 1, then I will get the second feature. You can see that it starts from 9.83 and 9.31. If I go back in the original data, it is 9.83 and 9.31. So in this way, we can not only find the samples from our data that belongs to cluster 1, but we can also extract the features as well. So these two steps are very important, that the first number or the first 0 represent the cluster number, and the second 0 represent the feature number or the column number. So this is the same step, that the sample of X from the second feature. Now here, this 0 represent the cluster number, and this 1 represent the feature number. So this is the second feature of X. If you run this cell, this is the second feature of X. And if you want to see in the form of columns, you can convert it very easily. So in this way, we have learned two important things after calculating ypred. So after calculating ypred, first we see how many samples belongs to cluster 0, or basically cluster 1. 0 is the index of the cluster 1. How many samples belongs to cluster 2, and how many samples belongs to cluster 3. Then we find those sample by indexing ypred is equals to 0 for our data sample. So here we get those samples which belongs to cluster 1. And we can also extract the features which belongs to cluster 1 by putting one more 0 after that. So here we can see that. Now it's time to plot. Now, first of all, before plotting, we can get the center of the clusters. Since we have three clusters, so these are the three centroid of the cluster. This is the first dimension. Because our data set is 2D, therefore the centroid are also 2D. So this is the first dimension or the first column or the first feature of the cluster, and this is the second dimension of the. Now we want to visualize the cluster. Before going through this code, let's run this cell first and visualize the cluster. So here there are three clusters, and we can see that this red is cluster 1. This is the centroid. This blue is cluster 2, and this yellow is the centroid of the cluster. This green is cluster 3, and this yellow is the centroid of a cluster 3. Now, how we plot this cluster? Let's go back to the code. So basically, we are using plt.scatter. We have seen this function so many times in this course before. So the first input is the first feature of X. The second input is the second feature of X. These are the size of data sample, or these are the size of the dots or the samples. This is the color of the cluster 1. The color of cluster 2 is blue. The color of cluster 3 is green. Now, the first 0 here in the first line indicate the cluster number. So this is first cluster, this is second cluster, and this is third cluster. These 3 0 indicates the feature number or the column number. These 3 1 also indicates the feature number or the column number. So this one indicate that this is feature 2, and these zeros indicate that these are feature 0. So basically we are plotting the 0 feature against the first feature against the second feature. So in this way, we do this for all three clusters. So this plt.scatter, this line of code will generate the cluster 1. So this 0 represent cluster 1. This line of code, the second line of code, will generate cluster 2. So this one represent the cluster 2 here, and this one represent the cluster 2 here. Now this line of code will generate cluster 3 for us. So this 2 represent the cluster number here, and this 2 represent the cluster number here. So it is very, very important to understand this concept, that what first 0 represent here and what second 0 represent here, because we are using this concept in our plotting. So in this lecture, we plot 3 clusters which we calculated from the elbow method. From the elbow method, we found that we need to implement K-mean algorithm using 3 clusters. Now we can see that these clusters are very well separated. So this is almost an ideal condition. There is no ambiguity about any data point. All the data points are strictly grouped together in their cluster, and they are tightly bound with their centroid. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So this lecture is a continuation of the previous 2 lectures. So we have already formed the clusters. We have formed 3 clusters. We get this value from elbow method. From elbow method, we see that the optimal number of cluster is 3. Now it's time to evaluate the performance of K-means, and we have to see whether the selection of 3 cluster was a good selection or not. So in order to evaluate the K-means performance, we need to import Kalinski-Harbach index. So this is present in sklearn.matrix, and the 2 input parameters are our data and the prediction. So if I run this cell, I will get the CH index score for 3 clusters, because we have performed K-mean clustering with 3 clusters. Let's run this cell, and we can see that for 3 clusters, the CH score is 3453. Now calculate this CH score for 2 clusters. So if we use 2 clusters in this project, what would happen? So we can see that if we put number of cluster is equals to 2, in that case, what would be the value of CH index. Let's run this cell, and let's run this cell to see the value, and we can see that this value is very small. We learn from our theory lecture that we expect the higher value of CH index. Highest the value of CH index, better is the performance of K-mean algorithm. Let's find CH score for 4 clusters. So you can see that number of clusters are 4 here. If I run this cell and if I see CH score, so this is also very high, 2523, but it is still less than with 3 clusters. Let's check for 10 clusters. Let's run this cell and see the CH score. So for 10 cluster, the value is 1731. So we see that we have selected 3 cluster in this project, which is a very good selection. For 3 cluster, our CH index score is highest as compared to any number of cluster. So this is the way of evaluating K-means performance. And we start evaluating K-means performance only when our algorithm is converged and we have clustered our data. So the data is clustered into 3 groups, and we can see that these clusters are very well separated, and this is approximately the ideal situation of the clustering. This is also verified with CH index score, and we see that when clusters are 3, our CH index score is higher as compared to any other number of clusters. So I hope you understand how to evaluate the K-means performance using CH index. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. In this lecture, we are going to implement K-means algorithm on another dataset. So this is the project 2 of K-means clustering. So in this project, we are going to apply K-means algorithm on another data, which is known as mall customer data. So this data has been downloaded from the Kaggle. However, this data is provided to you in K-means folder. So if you see your course folder, so you have mall_customer.csv file. So this is the dataset on which we are going to apply K-means clustering. So now the first step is to import all the necessary Python libraries. So these are NumPy, Matplotlib, and Pandas. So let's run this cell to import these libraries. Now, since this dataset is present in our course folder, so we need to mount the drive in order to read the dataset. So we have seen many times in the previous sections that how to mount the drive and how to set the path. So in order to save the time for this lecture, we have already mounted the drive and we have already set the path. Now you can see that the drive has already been mounted and here we have set the path. If you see the path is drive, my drive, course material, then unsupervised machine learning, and then K-mean clustering. So you can see from here also, inside the drive, there is my drive. Then inside my drive, we have a course material. Inside the course material, we have unsupervised machine learning, and then we have a K-mean clustering. So we have copied the path from here and we have pasted the path here. So in this way, we have already mounted the drive and set the path so that we can read the dataset very easily. Now, this is our path, and now we are going to read the dataset. So we can see that this is a dataset and it has 5 columns. If we see the first column is customer ID, then there is a gender. It is a categorical data, that is male and female. Then the age of the customers, annual income, and then spending score. So if we see the annual income, it is in thousand. That is, this is $15,000. This is also 15K, $15,000, 16K. You can see the unit, kilo, thousand. So this is the spending score, and that score is between 1 and 100. If a customer is spending more, then its score is high. So we can see that we have 5 column in this dataset, and now we are going to apply K-means clustering on this dataset. Now we can see that all these columns are not important in order to perform K-mean clustering. Like we have 5 columns, but we need 2 columns so that we can visualize the clustering as well. So we have selected 2 relevant columns. These are column 4, which are annual income and spending score. So now I have to extract these two columns from our data set. So we are using dataset dot integer location. We need all the rows. The first column indicates that we need all the rows of the data, and then 3:5. Since Python index start from 0, this 3 represent the fourth column. So we will extract column 4 and 5, and these dot values will convert data frame into numpy array. Let's run this cell and see the X. So we can see that we have successfully extract the two features, and we are going to apply K-means clustering on these two features. And these two features are annual income and spending score. So the next step is to apply elbow method to find the optimal number of clusters. So we know from the project 1 that in order to apply elbow method, we need to find WCSS, which is within cluster sum of square. So we run the for loop for 10 cluster, and then we find 10 WCSS values, and then we plot WCSS against the number of cluster to find the optimal number of cluster. So this code is 100% same as that code which you saw in the project 1 of K-means algorithm. So let's run this cell. And we can see that with the elbow method, we reach to the point where we can see the significant drop in WCSS. So if we start from the cluster 1, WCSS is very high. From cluster 1 to cluster 2, in this transition, WCSS drops. From 2 to 3 and 3 to 4, it also drops significantly. Then from 4 to 5, it also dropped. But after 5, if we can see that when the number of clusters are 5, after 5 cluster, the drop is not very significant. It is very less. And after 8 cluster, it becomes flat. So we can see that from this observation, we have seen that we should select 5 clusters for K-means algorithm. So this is the elbow method which helps us to find the optimal number of cluster using WCSS and number of cluster. So we observe that after 5 cluster, the change in WCSS or the drop in WCSS is not very significant. Therefore, we are going to select 5 cluster for this algorithm. Now we are going to apply K-means clustering. Here the number of clusters are 5, and this is our algorithm. And init auto means that we are going to select the random location of the centroid automatically. Random state is 42. Let's run this cell to get the predictions. And here are the predictions. Now we can see that these predictions are the values or the ranges from 0 to 4. 0 represent the cluster 1 and 4 represent the cluster 5. Now we have to plot 5 cluster here. So this code is also exactly the same as we saw in the project 1 of K-means clustering. The only difference is that in project 1 we had 3 clusters. Now we have 5 clusters. So we will assign different colors to all the cluster. Let's run this cell and visualize the cluster. Now we can see that we have 5 clusters with different colors. That is cluster 1, then we have cluster 2, then we have cluster 3, then we have cluster 4, and then we have cluster 5. These are the centroid of this cluster. Now what these clusters are telling us? Basically, these clusters are in 2D, and the dimensions are annual income and spending score. Now we can see that if we see cluster 1, so in cluster 1, there are those customer whose annual income is in the middle, and they are also spending in middle. In middle, their spending is not very high or not very low. Their spending score is around 50, and their annual income is around 60K. In cluster 2, we see that they are the customer whose annual income is very high, but they are spending very less. For cluster 3, we can see that their annual income is low, and they are also spending very less. If we see cluster 4, in cluster 4, we have the customer whose annual income is less, but they are spending more. Similarly, here in cluster 5, we have the customers whose annual income is very high, and they are also spending high. So how to do this? So the most important customers to be focused are the customers in cluster 4 and in cluster 5, because these are the customers who are spending high. So we need to give them more options for their shopping or for their scheme. So in this way, by plotting the clusters of a customer, we can observe which kind of customer need more focus as compared to other customers. So in this lecture, we learn how to apply K-means clustering on another dataset. So this time the dataset had 5 features. So we selected 2 features so that we can easily plot K-means cluster and we can visualize those clusters. First, we mounted the drive, then we read the data, then we extracted 2 important features, then we perform elbow method to get the optimal number of cluster. We see that in project 2, we had 5 clusters. We plot these clusters and we see and we visualize this cluster, and from the cluster we infer the results that the customer present in cluster 4 and 5 are those customers whose spending score is high as compared to any other customer. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So this is the project 3 of K-means clustering, and here we are going to apply K-means algorithm on another data. So this time we are not importing any data from outside, we are creating our own data. So the first step is to import all the necessary Python libraries, that is NumPy, Matplotlib, and Pandas. So let's run this cell to import all these libraries. Now here we are creating a random data, and then we will use this data to implement K-means algorithm. So the first step is here that I am creating 6 different data. So if you see, all these data has same size, that is 200 by 1. It means they have 200 samples and they have 1 feature or 1 column. And I am generating this using random.randn, that is all these data are generated from the normalized distribution. And finally, I am adding different values to them so that their magnitude should be different. So here I am generating 6 different data randomly using np.random.readn command. All these 6 data has same size, that is they have 200 samples and they have 1 column. So let's run this cell, and here we can print the shape. So we can see that the shape of x1 is 200 by 1. Basically, this is the shape of x2 also, and x3, x4, x5, and x6 as well. So we have generated 6 data randomly, and the shape of each data is 200 by 1. Now I am transforming this 6 data into 3 data. So first of all, I am doing the horizontal stacking of x1 and x2 to create x1. So this x1 is capital X1 and this is small x1. Now I am also stacking x3 and x4, the horizontal stacking, and I am creating another data known as x2. This is capital X2. Similarly, I am creating x3 by horizontal stacking of x5 and x6. So after creating 6 data randomly, I am transforming these 6 data into 3 data by performing horizontal stacking. When I will perform horizontal stacking, let's see the shape of the data and the data itself. So when I run this cell, I am printing x1 here. If I see x1, this x1 has 2 features now. And if I see the shape of x1, so shape of x1 is, it will be here, it is 200 by 2. So we can see that we started from 200 by 1. The shape of every data here is 200 by 1. So after horizontal stacking, the shape of x1 is 200 by 2. Here we had only 1 column or 1 feature, and now we can see that in x1 we have 2 features. Similarly, for x2 we will also have 2 features, and also for x3 we will have 2 features. So the shape of each x1, x2, and x3 is now 200 by 2. So we can see that this is the shape of x1. This also is the shape of x2 and x3. Now, finally, I am transforming these three data into a single data, which will be our final data. Now, I am using vertical stacking. Now, what will happen? We know that the shape of x1 is 200 by 2. If I vertically stack x2, so it will come under 200 by 2 and it will becomes 400 by 2. And then if I also vertically stack x3, the final shape of the x will be 600 by 2. So if I run this cell and see the shape, we can see that 600 by 2. So in final data, we have 600 samples and we have two features. So here we have created the data and now we are going to apply K-means algorithm on this data. So how we created the data? Basically, we started with 6 data, each of shape 200 by 1. Then we combine these 6 data to form 3 data by using horizontal stacking. The shape of each data here is 200 by 2. And finally, by vertical stacking of these 3 data, we form our final data, and the shape of this final data is 600 by 2. So in this way, we have generated our own data, and now it's time to implement K-means clustering. We know that before K-means clustering, we have to find the optimal number of clusters using elbow method. So the most important thing in elbow method is to find the value of WCSS, which is within cluster sum of square. Again, we are using 10 cluster to find the 10 different value of WCSS, and then we will get an elbow plot, and from elbow we will see the optimal number of cluster. So this code is exactly the same code which we saw in project 1 and in project 2 to calculate or to plot the elbow method. Let's run this cell to see the elbow. Now we can see that this is our elbow method, and now it is very easy for this particular project to find the number of cluster. We can see that here when number of cluster is 3, we have the optimal number. Why this is an optimal number? Because after this, the decrease in WCSS is very low. This line is almost flat. But before this, we can see that there is significant drop in WCSS value. So we have selected the optimal number of cluster equals to 3. Now it's time to apply K-means algorithm for 3 clusters. This is our method. Here we are randomly located the positions of the centroid, and here we are getting the predictions by fitting and predict K-means on X. So we have imported K-means. Let's run this cell. Let's get the prediction, and you can see that we have 3 cluster 1, then we have cluster 3, and then we have a cluster 2. 0 indicate the first cluster, 2 indicate the third cluster, and 1 indicate the second cluster. These are 3 cluster means, and here we are going to visualize the cluster. Let's run this cell, and we can see that we have successfully plotted the cluster, and we can see that the cluster 2, which is blue cluster, is separated from cluster 1 and cluster 3. But we can see that there is slight, or these 2 clusters are trying to overlap on each other. Now here I did not calculate CH index for this project. Now I am giving you a task to calculate the CH index. In project 1, you learn how to calculate the CH index using sklearn. So it's your task to calculate the CH index and see whether the selection of 3 cluster is good or not. Because we know that when we perform K-means clustering and when we have cluster, the final step is to evaluate the performance of K-means. To evaluate the performance of K-means, we have a metric known as CH index. We discuss CH index in detail in our theory lecture, and in project 1, we calculate CH index with the help of Python. So students, I am giving you the task to find the CH index for this project. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.